Hey, it's Stephen Lacey, executive editor of Latitude Media. And as you know, we co-produce Catalyst and the Carbon Copy with our friends at Canary Media. And we are barreling toward the end of the year, and that means that it is Canary Media's pivotal year-end donation drive. If you support this podcast, if you support the clean energy journalism you get every day from Canary, please make a donation to their newsroom. You can go to canarymedia.com/donate. Canary is a 501c3 nonprofit newsroom, so your financial support helps them survive and thrive and be a leading voice in the energy transition. And your donation is tax deductible. So again, go to canarymedia.com/donate to stand up and do your part. And if you want to support the journalism team at Latitude Media, just go sign up for our newsletter. You'll get all of our reporting and upcoming research on the frontier trends in renewables, storage, virtual power plants, carbon removal, and more. It's at latitudemedia.com/newsletter. So go support Canary Media with a tax-deductible donation. Go support Latitude Media by signing up to the newsletter. And thank you very much. Now, on to the show.
From the studios of Latitude Media and Canary Media.
I'm Shayle Khan, and this is Catalyst.
There are ways that how we license reactors could be modernized to meet the needs of these advanced reactors that have all these passive safety features, but I don't think it's a silver bullet.
With new nuclear, it's all about physical safety, not an engineered system. But that's splitting atoms.
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shayle Khan. I invest in revolutionary climate technologies and energy impact partners. Welcome. All right, so I've thought a lot about this one because it's complicated to talk about, but it also seems really poorly understood to me, which is sort of how should we be thinking about nuclear power, or specifically nuclear fission? It's a space with obviously no shortage of polarized views. On one hand, you have the nuclear is the future crowd, which thinks that the U.S.'s current and recent inability to license and build new nuclear at any real scale is essentially the single dumbest thing we've done as a country with regard to both energy and climate. On the other hand, there's the crowd that thinks that nuclear is at best a very expensive source of power and really probably just a waste of time. We need to be focusing on other technologies to decarbonize. And these are both frustratingly loud voices, in my opinion. But for me, and I think for a lot of people, it's more complicated. Would it be great to have a whole lot of new nuclear providing clean, firm, affordable baseload power? 100% yes, no question. So what is stopping us from doing that exactly? Well, obviously, one answer lies in the regulatory realm. But the second answer, and the one that actually interests me more, is the question of cost. And this is where I feel like the narrative is kind of confusing. Depending on the lens that you use, nuclear power is either inevitably incredibly expensive and thus not worth pursuing, or it can be incredibly cheap if only we get out of our own way. And there's some evidence on both sides of this. On the expensive side, you can look at the cost overruns that have hit basically every recent reactor development in the United States and in some other countries, whether traditional reactor types or so-called small modular reactors. On the cheap side, you can look both at the past, when we have actually built pretty cheap nuclear, and at the rest of the world today, where in some countries, costs have been going down and continuing to get lower and lower. So I wanted to dig in specifically on the cost of nuclear fission. What actually drives it? And what could we say about those costs if and when development really starts to pick up the pace here? My guest this week, Jessica Lovering, literally wrote a paper on this topic, one of the few, a few years back, and she monitors the nuclear industry as closely as anyone. So she's exactly the right person to talk to about this. So no further ado, Here's Jessica. Jessica, welcome.
Hi, thanks for having me.
I'm excited to talk to you about the cost of nuclear, which is the topic that we want to talk about here. I think it's difficult to talk about the cost of nuclear without talking about a bunch of other things related to nuclear, obviously regulation and things like that. So we're going to see as much as we can how to talk about all of that through the lens of cost, ultimately, which is one among a bunch of variables that are important, I think, as we think about the future of nuclear fission. But before we get directly into cost, I think we're going to talk a lot about the global context here, because I know there's a big difference between what's going on here in the US and what's going on in lots of other countries. So let's start with the global context. Where in the world is there a lot of nuclear development activity today, and where is there relatively little?
Yeah, so I think, from a US context or US audience, nuclear can feel pretty stagnant because we've barely built any nuclear in the last 30 years. But globally, there's huge growth in deployment of nuclear. So nuclear is mainly being built where there is rapid growth in demand for electricity, because nuclear is very large-scale technology. So East Asia, South Asia, Central Asia primarily, places like China, India, South Korea. But there are also over 30 countries that are looking to develop their first nuclear power plants. We call them these nuclear newcomers or nuclear aspirant countries. This is a lot of lower income, middle income countries that are still industrializing. So it's a lot of places in, across Asia, but also sub-Saharan Africa, Central America, South America. So there's a lot of places that are interested in nuclear. And some of the countries that have joined recently that have started or have nuclear under construction, United Arab Emirates has brought online, they're about to bring their fourth reactor online, but this is their first nuclear power plant. Each reactor is huge, so it's 5.6 gigawatts of power, and it'll be 20% of
That's one project?
One project, 4 reactors.
5.6 gigawatts for a single project?
Yeah.
What's the largest nuclear project in the world?
I believe it's in South Korea, and it's 8 reactors. So, yeah, they can get pretty big. The largest power plants in the world are all nuclear power plants. The largest power plant in the U.S. is a nuclear power plant. And they can, generate huge amounts of electricity. But I think what's crazy about the UAE project is that this is 20% of their electricity when the project's complete. And it took, a decade to get it up and running. Other countries that have their first projects under construction, Turkey, Egypt, Bangladesh, there's a lot of interest in Eastern Europe. We can come back to that, like Romania and Poland. But we're also seeing, places that already have a lot of experience with nuclear are looking to expand or build new projects in light of recent energy crisis after the Russian invasion of Ukraine and the shutoff of Russian gas. So places like Sweden, the UK, even Belgium, which had a planned phase out of nuclear power, putting their phase out on hold for 10 years. So a lot of places are rethinking nuclear, even in, wealthy countries that already were reconsidering nuclear, looking to end nuclear in favor of renewables are now rethinking that. So there's a lot in flux right now.
So if we were stepping back and just looking at the global picture, what would the curve of nuclear development have looked like over the last 30 years or something like that on a global basis?
Yeah. So if you look at just the deployment curve, it really was fast in the 70s and 80s, and it has leveled off. It's growing again, but it's pretty slow, and it's definitely slow in comparison to just growth in energy demand overall. It's not at the scale it was in the 70s and 80s where there was this huge explosion. That's a terrible term. Huge growth in nuclear.
I'm sure working on nuclear all the time, you have to be particularly careful about the random terms that you use.
So we don't see that kind of rapid growth, but there is still growth. There was a big drop after Fukushima. A lot of countries closed reactors, short-term or permanently. And so we're seeing a rebound from that now, but it's slow growth. I think, unlike what happened in the U.S., there were still places that had big nuclear fleets building in the 90s and early 2000s. Like France and Japan kept building nuclear. But places like the U.S., which still has the largest fleet of nuclear power in the world, really stopped in the 80s.
Okay, so one of the reasons I wanted to talk about the global context is because, as I understand it, the cost of nuclear power, and the capital cost of developing nuclear projects is quite variable from location to location. And so this is sort of the first key point. So how variable? Like if I was looking at the low end and high end globally of what it costs to build a nuclear reactor or a nuclear project, like how different are those costs from each other?
That's a great question, as it is quite a big range, whereas something like a solar panel, it's pretty similar globally.
Yeah, there are differences, right? Like the cost of modules doesn't vary that much. It varies a little bit globally. The cost of installation does vary. And so, at utility scale, there's meaningful variability, but it's not day and night. It's like once you get down to residential solar, then people will point out to you that it costs like a third as much to install in Australia as it does in the US. But there's some variability. But my sense is that it's the variability is higher in nuclear,
Yeah.
I think.
Definitely. And while there used to be a lot more trade in nuclear, like the US used to export a lot of commercial nuclear around the world. It's more today built like an infrastructure project. So it's very country specific. So the cost can really range. I would say that the cheapest nuclear in the world, and I'm so glad that your audience can understand if I say dollars per kilowatt, is in South Korea, and that's about $2,200 per kilowatt.
And that's the cost of reactors that have been built recently. This is like current day. So $2,200 a kilowatt. So that's a good benchmark for us to start talking about. So that's the low end. What's the high end?
Yeah, and I was just looking up it can be hard to get these costs in this number for these large projects that took decades to build. But the Vogtle project, which just finished in the U.S., is probably at the high end. I think the project that just came online in Finland is probably up at this level as well. It's about $8,000 per kilowatt, so 4 times more. Yeah, so it's a big range. And the U.S., in terms of thinking about like a moonshot, like what sort of goal would you have for the cost of nuclear? Under $2,000 per kilowatt is really the goal that people think to make nuclear cost competitive. With natural gas, it would need to be under $2,000 per kilowatt.
Okay, so that's useful. So a moonshot goal would be under $2,000 a kilowatt. Can you translate that? Obviously, it's dependent on the cost of capital and other things, but like, what is the dollar per kilowatt hour cost that targets?
Yeah, that's a good question. I think this is a rough estimate. I think that's under $60 per megawatt hour.
Yep.
Yeah, and I will just point out, I think something that's really important. We think about nuclear as being really expensive, and it is in terms of total project costs. But for existing nuclear power plants, the electricity is some of the cheapest we have in the world. In the U.S., existing nuclear power, the electricity generated is the second cheapest, only after hydroelectric. Again, this big infrastructure project that was really expensive at the beginning, but now is just churning out tons of electricity. France has the cheapest electricity in Europe, and it's 80% nuclear.
So this gets to one of the things I wanted to talk about, though, because you hear that and but then we say a moonshot goal for the cost that we should be shooting for in the future is works out to $60 a megawatt hour or something like that, which would be cheap for clean baseload power and certainly like in the money, but not as cheap as what you're describing, not the cheapest thing besides hydro. So that implies that historically, this is the other context, there's a global context and then there's a historical context. That implies that the historical cost of nuclear, or the cost of historically developed reactors, I guess I should say, is even cheaper than the future moonshot. Is that right?
Yeah. It is true that the reactors that the U.S. built in the early days, in the 60s, were much cheaper than the ones today. There's a lot of reasons for that. But also, it's similar to what South Korea is building nuclear for today. So it's not like the standards are different. It's a lot about how the industry is structured. And so really what makes nuclear cheap and where nuclear is cheapest, whether you're looking at history or where it's cheap currently, it's where countries and utilities are building a lot of reactors in series of a standardized design. And not just you're learning with the technology, but the industry is learning, the workers are learning, the regulator is learning, and you have those sorts of economies of multiples. And that's really what nuclear has lacked in the US, Europe, most places that aren't building a lot of it today.
And so in the places where we are seeing more of it get built, take South Korea as an example, are we seeing a predictable cost curve?
Yes.
Right now?
Yeah, you do in South Korea. Mm-hmm. And that they started out much higher, actually, more like $4,000 or $5,000 per kilowatt, and came down. And you do actually see learning in France in their history, but it jumps up every time they introduce a new reactor design, and then they learn. So it's kind of like first of a kind, and then they learn and get better. So yeah,
okay,
it's what you'd expect,
right? And then I guess the other place that we haven't really talked about, you mentioned that it's on the list of places that's building a bunch of nuclear, but we haven't talked about it in the context of cost. But I think you hear about a lot is China. Do we have any sense, first of all, how much nuclear is China actually building? And second of all, what do we know about the cost of that nuclear?
Yeah, so China has the most nuclear under construction of any country. It has about, I think, 22 reactors under construction right now. When those are complete, actually just when a few more come online, they will surpass France as having the largest fleet of nuclear, so the second largest in the world after the US. And they're building a ton of nuclear. There are some estimates from the International Energy Agency on costs in China, but we really don't know. It's state-owned utilities, state-owned developers. But we do know how long it takes them to build projects, because when you start construction and when you end construction, that's reported to the International Atomic Energy Agency, which is kind of like an international regulator, not entirely. So we know the construction duration of projects in China, and they are following a trend that looks like South Korea in terms of how long it takes. And time is a pretty good proxy of cost, as you can imagine. So from our estimates, we can say China's probably building at about $2,500 per kilowatt, so not quite as cheap as South Korea, but nowhere near the US. And again, that's probably because they're building a lot of the same design. China's also had a much larger focus on indigenizing technology. So they started by importing nuclear designs from France, from the US, and they had technology transfer agreements. So they, leased the design, and then they worked on developing their own domestic design. And then they're working on indigenizing the supply chain. So now their projects are 80%, the components are manufactured in China, and they're working towards 100%. So they've put more of a focus on that, and that maybe made their projects more expensive in the short run. But for them, it was worth it because they wanted to bring the technology and the manufacturing in-house. I will say, from what we know, a lot of the cost of nuclear is not necessarily in like concrete and steel. It's a lot of like engineering and design costs and project management. And that's one reason, this is not my specialty, but there are some case studies that look at what's going on, what South Korea is doing right. And a lot of it comes down to really good project management, which is something that's harder to kind of export. But it does make a really big difference. And that's where having a standardized design really helps.
Yeah, that gets to what I wanted to talk about next, which is you hear about nuclear costs as it's a single data point, whatever dollars per kilowatt ultimately. You could talk about length of time as well. But I've always been curious to dive in one level deeper than that and like figure out what actually does comprise what's the pie that makes up that X dollars per kilowatt ultimately. I mean, you just alluded to it somewhat, but can you kind of walk through what are the major categories of cost and maybe, I don't know, take whatever representative example you want and sort of how large are they proportionate to each other in a typical development?
Yeah. So I'll start with the cost of electricity, and then I'll break down the capital cost. But cost of electricity, the cost is almost entirely in the capital cost. So it's more similar to wind, solar, hydroelectric, and doesn't really look like a fossil fuel plant. So even though it's a thermal generator, the fuel is a very small proportion of the cost. So unlike a wind farm or a solar plant, the capital cost is really large because we've typically been building huge plants. So that's really important. If we want to bring down the cost of nuclear, you have to bring down the capital cost. Now, what actually goes into that cost? So I actually pulled up this report from 2012, which is one of the only breakdowns that you can find. And so this is for a AP1000 estimate in the US. And about...
Describe what AP1000 is.
AP1000, so yeah, that's the reactor that was built in Georgia at the Vogtle plant. It's a Westinghouse design. It's 1.1 gigawatts, huge. Has some innovative features, has some modular components, but it's still a large stick-built nuclear power plant. So for a plant like that, about half of the costs come from the power plant outside of the reactor. So what's like the yard, the cooling infrastructure is huge. And installation. So a lot of that groundwork. So nothing to do with nuclear. But there are a lot of regulations on that concrete and steel. The actual nuclear component, what's called the nuclear island, so that's like the reactor, the pressure containment structure, that's only 12% of the total cost. So that nuclear part is very small. And then a huge portion, 35%, is engineering, procurement, construction management, and owner's costs, which is my interest during construction and things like that. So it's not a lot of the actual nuclear part. It's a lot of this other construction thing. And that's, I think, something to remember when we're asking, why is nuclear so expensive, is that they're still built like large infrastructure projects. It's not like building a car or an airplane. It's like building a highway or a hydroelectric dam or a bridge. Each one's very unique. And so these, secondary sort of ancillary costs really add up.
So that obviously gets to, there's a series of new technologies that are aimed at solving sort of that problem, right? Which is, let's figure out how to make these less like infrastructure projects and more like rinse and repeat things, because as you said, it's not the cost, turns out it's not the cost of the reactor that really matters. It's the cost of, one, everything outside of the reactor, and two, the, soft costs, so to speak, the engineering and construction labor and all that kind of stuff. I guess based on what you've said so far, I could see that going two directions. On one hand, great, it's attacking the right problem from a cost perspective. If you can do it, maybe this is why, the next generation should be smaller, and this whole concept of SMRs or whatever it's going to be. So on one hand, it seems like that's attacking the right problem. On the other hand, what you said before about how to drive costs down is basically we build a lot of the same reactor type over and over again, but instead, at least in the US, what's happening right now is you've got a bunch of contenders with a bunch of different reactor technologies who are all simultaneously trying to squeeze through the window to get to first commercialization. And so if it works, but 15 of them get to first of a kind, does that mean that every one of them starts at the top of the cost curve and we have an even harder time driving down? So I'm curious how you think about that with this raft of new opportunities.
I definitely hear that argument. And I think it's something to keep in mind, because I often give this analogy of how we could do nuclear better in the future is like wide body aircraft. So like Boeing and Airbus. And what's interesting about that example is it's really just Boeing and Airbus. It's a duopoly. And honestly, the market could really only support one of those companies if it wasn't that both the US and the EU are heavily state supporting those in different ways, because they're critical. So for nuclear, I think it's an open question of how many companies there could be. But at this point, there's a sense, and this comes from nuclear's history, that we don't want government to choose which design, because there's been, this phrase of government shouldn't pick winners. And I think that is a legitimate concern with nuclear, that what's gone wrong in the past is that nuclear power plants were designed by engineers, for the needs of the military. They weren't always chosen, the design wasn't always chosen with sort of market needs. And that's where a lot of these companies that are working on new nuclear technologies are focused on what could be competitive in liberalized power markets, and how do we meet the needs of those markets and the customers, which is utilities. And so I don't think we're going to have, 8 companies building thousands of reactors in the US. But I do think we're going to get demonstrations of several, and we'll probably see which ones work and some of them aren't going to work. And I think that's what we've seen with, the recent cancellation of the first NuScale project. It didn't work out, and I think that's okay. There's still a robust industry with lots of other companies, but we are going to need to sort of have some built, get able to see how much they cost, kick the tires, and that's when orders are going to start coming in. Because that's something with, when Boeing designs a new aircraft like the 787, they have an order book of several hundred airplanes before they even start manufacturing. And that's really what the nuclear industry needs to be successful. So, okay, coming back to modularity and whether that's going to work, I think there is a lot of skepticism that new nuclear designs will be cheaper because it feels like a promise that's been made and broken a lot. This idea of nuclear is supposed to be too cheap to meter. And we've seen with Vogel and these projects in Europe, like in Finland and France, just going way over budget. But there are really good reasons to think that these new technologies will be cheaper. But they have to be built first to prove that case. So modularity and factory fabrication are huge. And it's uncertain yet if it'll work for nuclear, but we've seen it work for all other energy technologies. And there's two really good papers, which I will share with you. So one is Wilson et al. 2020 and Swartz et al. 2020. But they both look at the size of energy technologies and their learning rates. And they find that across all sorts of energy technologies, batteries, generators, the smaller they are, the faster they learn. And that just makes sense. But there's no reason to think it wouldn't also make sense for nuclear. And then the other thing, a lot of these technologies that we call advanced nuclear, it's a lot of different technologies. I can talk more about them, but the big thing is that a lot of them rely on passive safety. So it's safety that's derived from physical processes, not engineered systems. And why that matters in a simple way to explain it is that you can have much simpler engineering, so it reduces complexity in the design, and that can also make it cheaper to manufacture and make the operations and maintenance simpler and cheaper as well.
This may be impossible, but can you, in layperson's terms, explain the difference between physical processes that deliver safety versus engineered systems that deliver safety?
I have a good example that is tested on my mom, who has explained it to her bowling team. So there's many
Perfect.
different aspects of passive safety, but here's one that I think most people can grasp. So if the reactor gets too hot, you need to cool it. And so the way that's done in a lot of traditional water-cooled reactors is with pumps. And you need to have these really robust pumps that won't break down, and then you need to have redundant pumps in case they do break down. So you might have 4 pumps when you only need 1. And they have to be able to operate at really high temperatures and with radioactivity and things like that. So these really over-engineered pumps. Now, with a lot of the advanced reactors, they rely on convective cooling to move that heat around. So that is like what happens in your tea kettle or your soup pot, where hot stuff rises, and then when it cools down, it drops down. And so this convective cycle moves the heat through. And they do that through engineering and through the types of coolants they're using. So they don't have to have all those heavily over-engineered pumps to move their coolant around.
That works. If I were on a bowling team, I feel like I would understand that. Okay, that's useful. I guess this is sort of getting to it, but just to ask it directly, I mean, the other thing you hear a lot, and particularly so when I'd say nuclear advocates in the U.S. talk about like, why aren't we building? So here's the debate that I see, right? Like, and where I feel like people talk past each other a lot. Nuclear advocates say we should build more nuclear in the U.S., and we're holding ourselves back from doing so. Nuclear opponents say, look, set aside the safety thing, it's too expensive. And we have data points to suggest that it's too expensive. Nuclear advocates respond, it's expensive because of how we regulate it in the United States. And because of that, we haven't been able to get down the cost curve. And so that gets to this question of like, are we able to ascribe some amount of that cost, that total cost, to regulation? I mean, clearly the cost to get a new reactor design licensed is very high, but maybe even setting that aside, how much of the cost associated with the capex of a nuclear plant is because of how we regulate nuclear in the United States versus how they do, say, in South Korea or somewhere else?
Yeah, so I think it's one factor, but it's not the dominant factor. And you can see this in, that huge range of costs that I cited in the beginning, $2,000 in Korea, $8,000 in the US. It's not that South Korea has a vastly different regulator. It's actually modeled much on the US. And the US regulator, the NRC, is considered the gold standard, and a lot of other countries follow our example. So I think there are ways that how we license reactors could be modernized to meet the needs of these advanced reactors that have all these passive safety features. But I don't think it's a silver bullet. And I think where I'm in the middle between the nuclear advocates and the nuclear opponents is that I think the industry has made mistakes in terms of how they've managed construction projects and supply chains. And a lot of that could be done much better. And there's, challenges of just they scaled up too fast. And so they didn't understand how the safety was working. And they had to go back and change designs as they learned more and sort of things like that. I think one thing that I really like to emphasize that I think people don't think about is that what's really been missing with nuclear in terms of policy to help bring down the costs is that demand pull policy. And so this is why you see that nuclear is cheaper and gets cheaper over time in places that have a lot of growth in demand for electricity because the plants are really needed. So there's demand for them. And that was true in the US as well. That's when we built a lot of the nuclear, but cost didn't come down for a lot of reasons. But the US hasn't ever really had policies to create or incentivize demand for nuclear or even for low carbon energy until quite recently with the IRA. Unlike renewables, which have benefited from 3 decades of different kinds of incentives, production tax credits, investment tax credits, that really caused that pull and led to a dramatic decrease in price. I think, if you look at the cost of solar in the 70s, it was like $100,000 per kilowatt. And we never thought it would be this cheap. And it's been amazing. And that's due to a ton of innovation. But that innovation was really induced by these demand pull policies and these renewable energy or renewable portfolio standards that drove demand at the state level, and all sorts of different policies across countries. So I think that's where there are some of those incentives starting with the Inflation Reduction Act, and also some states are changing their policies to focus on clean energy mandates that are inclusive of nuclear. So we might see that change.
So just to parrot it back to you, I guess what you're saying is that the cost, the embedded regulatory cost is not like the biggest driver of CapEx of nuclear in the United States. However, what is probably the biggest driver of the fact that the United States has extremely high costs for nuclear, at least from the very, very, very few reactors we've built any time recently, is that we don't have volume. And we don't have volume in part because we don't have demand pull policies, probably also in part because the regulatory construct has made it tough to license reactors and so on.
Yeah.
So it's all circular.
Yeah, and I think, for what will be needed is if we're doing really modular plants, like factory fabricated reactors, that will definitely need a regulatory change because we don't have those sorts of bulk licenses like you do for aircraft manufacturing. You're not licensing like each individual aircraft as if it's a brand new project. And so that's definitely needed. But I think for these first demonstrations, the companies are, able to muddle through with the current system. And the regulator is, acting in good faith. They're trying to get up to speed. They're doing the best they can. They need more resources in terms of funding and just people as well. So, yeah.
Okay, so what is your take on nuclear in the U.S. then? It's an interesting moment that we're in right now. As you mentioned it, right? But recently in the news was this NuScale project getting canceled, this UAMPS NuScale project, which is a big deal as I understand it, just in part because NuScale is the first new reactor to get design certification in, you tell me, 30 years or something like that. That was the first project that they were going to develop. They had first cost had ballooned. So to our point that we've been talking about, they made an announcement, I think last year, that costs were going to be $90 a megawatt hour instead of 65 or something like that, and then maybe even higher. And then they couldn't get enough subscriptions. And so the project's canceled. So, you mentioned there's still sort of a vibrant ecosystem, but I guess the question is what do we make of that? Is that just an anomaly or indicative of something broader? And then I guess second, to the point you made before about, so maybe what we do in the US is we get 15 new reactors demoed, and then we need to kick the tires on them and see what's cheap, and then the order book will start coming in. Like, what's a realistic, in your mind, time horizon during which we can expect to kind of get the gears really turning on nuclear in the US? I'll add one more point, which is that the one thing we do have going for ourselves now is a resumption in growth in electricity load, which, as you said, has been a hallmark of the countries that have really shown the ability to scale nuclear. So we may get that back. But yeah, what do we make of the NuScale thing? And more broadly, like, how long, if it happens, how long is it going to take us to get momentum?
Yeah, and on top of, starting to see growth in electricity demand, whether it's from electrifying industry or transportation or making hydrogen, there's also a lot of states pushing for more aggressive decarbonization policies. So we're starting to see more, serious ambition around clean energy. And so I think that's all positive for nuclear. With NuScale, it's really disappointing for sure, but I don't think it's any sort of death knell. And the reason is there is just this vibrant, thriving, advanced nuclear industry. There's lots of other designs. NuScale was, it had a lot of government support over the last decade, but it was a very different kind of project. It was water cooled. It looked more like a traditional nuclear power plant. It was also, the plant was going to be quite large. It was closer, it was modular units, but being built in a 12-pack. So looked more like 700 megawatts. So that's a very big, power plant that you have to construct. So the other reactors going forward, none of them are water cooled. They're all very different technologies. And so, I'm pretty optimistic. I think a lot of these, there's, maybe 6 or 7 that are seriously working with the regulator to get licensed for their first projects. And I think we'll probably see ground start to get broken in maybe the next 5 years, and probably, I would say, a handful of projects coming online before 2030.
That's actually pretty fast. I mean, if you're saying a handful of projects beginning construction in the next 5 years, we're at the end of 2023. So if anything is going to come online by 2030 at this point, that's 6 years from now.
Yeah, and what helps is that some of these projects are really small. So not just SMRs, small modular reactors, but micro reactors. So this is projects or reactors under 10 megawatts. So some of these are even on the order of 1 megawatt, which is tiny. That's like smaller than a wind turbine. And they can fit in, a shipping container or two. So that's how we might see some, commercial demonstrations really fast is, even if it's a new technology, it just can't take that long to build something so small. So that's kind of how we could see an acceleration in innovation and demonstration of these new technologies. But for the bigger technologies like TerraPower's project in Wyoming, that's a pretty big power plant. And so it's going to take, different paths for these different projects. But to your question earlier about, is it too many? Is it too much diversity? Do we need to sort of narrow it down? I think there's a lot of different markets, and there might be sort of right sizing. So different nuclear tech will work better for different markets. There still are these large investor-owned utilities. They might still want a really large nuclear power plant, maybe to replace a large coal plant they have coming offline, or replace an aging nuclear power plant they want to shut down. And then you might have a rural electric co-op, which would love a 1 megawatt microreactor to help back up their wind and solar, or a hospital that could take a 10 megawatt reactor for on-demand power. I think there's just a lot of different markets, and those markets haven't necessarily been able to access nuclear in the past, but now they can. So it's a very different business model and way of thinking about nuclear.
I guess final question for you. The other thing that strikes me as a challenge for the resumption of nuclear in the U.S. is not necessarily just that it's higher cost for first of a kind or first few of a kind. It's the cost uncertainty, right? Like that seems like the biggest challenge. If I'm going to be a buyer, if I'm going to I'm a utility and I'm contemplating adding nuclear into my integrated resource plan, how much certainty can I really, what are the error bars around the cost that I'm going to assume? And that's what seems like it has been the challenge of late. Projects that have gotten built like Vogel, projects that didn't get built like the NuScale one, these surprise 50, 100% increases in cost relative to expectations. Like, I would think it would make it difficult to plan around that for a big capital investment.
So let me give you some examples where these companies are thinking more about market needs. That's definitely something they're thinking about. So coming back to the aircraft example, as I said, Boeing has this long order book of aircrafts even before they manufacture the first one. And how they price them is not what it costs to manufacture it. It's somewhere sort of halfway down the learning curve. So the first few hundred, they sell at a loss, but they need to commit to a price, a fixed price to get those orders. So you might see something similar like that, probably not for the first of a kind, but for the second, third, fourth of a kind, saying, okay, you are going to pay, $3,000 per kilowatt fixed price, no matter what it costs us.
That one is a good argument for smaller project sizes, right? Because nobody's going to stomach selling, gigawatt scale projects at a loss for very long. But you could do it for 10 megawatt projects.
And then some other companies, particularly more on the microreactor side, are looking at doing more like a build, own, operate model where they'd be selling electricity through a power purchase agreement, which, looks very different. So the company would be maintaining ownership of the nuclear power plant. They'd install it on site and they would just sell the electricity at a fixed price. So that would really mitigate risk, especially for smaller utilities, municipal utilities. That's something they could stomach.
Although, isn't that exactly what the NuScale project was going to be? And the problem was that the price ended up being the price of power, not just the CapEx, ended up a lot higher than expected?
Yeah, but the communities were given the option to opt out of the project, and they did. So
that was a mistake, right?
It looks bad, but it was a success, at least from the community's perspective. They weren't sort of stuck with an expensive project. Yeah.
Right. They weren't on the hook with an albatross. Yeah, that's a good point. Okay, so I guess wrapping up then, how long have you been focused on nuclear? How long have you been spending time on nuclear?
Oh, I think since 2011, so quite a while now.
Okay, so a dozen years looking at nuclear in the United States. Where are you on the optimism spectrum today relative to where you have been over the last 12 years?
Yeah, I think just in the past year, I've seen a lot change. So I live in California, and seeing, Diablo Canyon was supposed to shut down this year and next year, and seeing a very liberal Democratic governor change the plan for nuclear in California, I think that's a big thing. And you're seeing this in a lot of other places, like Japan and Sweden, changing course on nuclear because of the realities of energy needs and natural gas, particularly after the Russian invasion of Ukraine, really got people thinking differently about energy security. It kind of pulls us back to this 1970s energy crisis mentality. But that is really where nuclear was successful, was supplying this huge displacement of fossil fuels in the 70s. And so I wouldn't have been this optimistic maybe a year or two ago. And then also seeing this much more ambitious commitments on climate. I think it's, definitely not fast enough, not enough investment, not enough closures of fossil fuel plants, but it's better than where we were 2 years ago. So, I am not like some nuclear advocates. I'm so excited by the rapid deployment of solar and wind and batteries. And seeing nuclear get to play a growing role, even if it's a small role, I think is really positive for making progress on climate change.
Jessica, thanks so much for doing this. This was very insightful for me.
Yeah, my pleasure. It's great talking with you.
Jessica Lovering is the co-founder and executive director of the Good Energy Collective. She's also formerly the director of energy at the Breakthrough Institute. This show is a co-production of Canary Media and Latitude Media. You can head over to canarymedia.com for links to today's topics. Latitude Media is supported by Prelude Ventures. Prelude backs visionaries accelerating climate innovation that will reshape the global economy for the betterment of people and planet. Learn more about their portfolio and investment strategy at preludeventures.com. This episode was produced by Daniel Waldorf, mixing by Roy Campanella and Sean Marquand, theme song by Sean Marquand. I'm Shayle Khan, and this is Catalyst.